Yeah, when I was younger, I was interested in a whole bunch of other things, but when it was time for me to pick something to study in college like you, I actually decided to go with mechanical engineering because I wasn't sure back then whether I would actually be able to land a job in the aerospace industry. So I wanted something that was very broad that would give me a lot of options. I also really loved astronomy, but back then, this is pre-internet because I am that old. I wasn't sure what astronomers did, like who would pay you to go out and stare at the stars. I really just didn't have a good concept of it, which is one of the good reasons why I chose engineering. These days now, if I had been in your shoes, I might have decided to go be an astrophysicist or study astronomy because that's really my first love. But I studied mechanical engineering. I went to the University of Kentucky for my undergraduate degree, and then I went to Georgia Tech for my master's degree. And I still stayed with mechanical engineering with a focus of controls and vibrations. And then, fortunately for me, JPL came to a career fair there. I had done some internships at NASA Langley when I was at University of Kentucky, which is really very fortunate for me. It was my first like toehold in the world of aerospace engineering. I worked there for a fall and then a summer and then a spring and then a summer and then did summer working at GE Appliances in Louisville, Kentucky, where I'm from, before I went off to grad school. But when I was finishing up my grad school degree, JPL came and did a career fair there and or came to participate in the career fair there. And I was able to give my resume to them and they invited me out to an interview. I interviewed with several other places as well. But of course, JPL was where I really wanted to work. And so I was very fortunate to get hired right out of my graduate degree, starting in systems engineering at the Jet Propulsion Laboratory.
So, did you realize that you wanted to be in spacecraft operations from then on, or did you have to kind of build your way up to that? And then were there like an experience that led you to want to do spacecraft operations?
Yeah, I kind of had no idea, to be honest. I just wanted to have something to do with helping to design and build and test or whatever with spacecraft. And it was good that I didn't, in hindsight, it seemed good that I didn't kind of have an idea because then when I landed at JPL, they could just kind of throw me in anywhere. And I was really interested to try whatever it was that they had to offer. I had never heard of the discipline of systems engineering before I was hired into the systems engineering division at the lab. And so I learned from them that systems engineering was about understanding how all of the different aspects of a spacecraft work, or all of the different aspects of a project, or whatever level you're working at, and how to find potential problems in the design so that you can make the design such that everything works as a whole, how to find problems when you are building and testing it so that you can fix them in a way that doesn't make something else worse. And then when you're operating a spacecraft, when there are problems, you have fewer knobs to turn because you can't mess with the hardware anymore, but how you change the software or how you change the way you command it in order to do what you want. So I was just very lucky to land in the systems engineering arena. It turned out to be perfect for me because you need to learn a whole bunch of things about a variety of things, which really kept me interested. And you also get to work with a lot of different people. And I like people, and not being locked in a room with my own computer all day was great. So interfacing with people, finding problems, solving problems. Yeah, I had no idea that's what I would like, but it was great when I wound up there.
Yeah, amazing. So going into academic versus real world systems thinking, how does systems engineering change once that spacecraft is actually in flight and in the air?
It changes dramatically because you have a little bit less insight into what's going on with the spacecraft. All you have is the data that it's sending back, and you can't, for instance, go plug in an oscilloscope to see what's
Mhm.
going on with voltages because that's not a thing. So all you have is whatever you had programmed in it to send you back. So it's a little bit more of a more challenging mystery hunt to figure out what's going on with the spacecraft. And then once you can figure out to the best of your ability, the things that you can do about it are limited too. For instance, you have a spacecraft that's in cruise on its way to Jupiter, just like Europa Clipper is right now. If, say, a component on the spacecraft is getting a little warmer than you expected it to be, there's only so much you could do. Maybe there's a heater on that part, maybe there isn't. Maybe you can turn it farther away from the sun, but maybe you can't because you also need to point your antenna at the Earth. So it gives you more constraints to work in and makes your problem solving process a little more challenging and a little more interesting, in my opinion.
So what exactly is telemetry, or is that how you say it?
Yeah, sorry. I should remember not to use technical words. Telemetry is just a fancy word for data that a spacecraft is sending back. So when we have a spacecraft up there, we have a whole bunch of things that it can tell us from the temperature of all the different pieces of it.
Mhm.
It can tell us what voltages the different electric components are. It can tell us what currents are. It can tell us whether something is powered on or off. And there's like more than 10,000 different kinds of telemetry, we call it, little data points that our spacecraft can tell us about its state.
So, like, let's say some unexpected behavior shows up in the telemetry.
Mhm.
What do you do in that scenario?
Yeah. Yeah. So what we first do is try to figure out, okay, what area of the spacecraft is that telemetry from? Is it from a thing that the spacecraft uses to figure out where it is? We call that attitude knowledge. Is it from something that is related to temperature? Is it one of the science instruments? And then we make sure we have the person or people who are most familiar with that part of the spacecraft come get in a room with us so we can talk about what we saw and see if we can figure out what it means for the health and status of the spacecraft. And you especially want to know right away, is it something that is changing, something that could be getting worse, and so you want to like move quickly in order to do something about it? Or is it something that's pretty stable and so that you have plenty of time to go figure out what to do?
So, Mars missions, they involve long communications. Like how does that kind of shape the fault protection and how engineers like think about risk?
Good question. Yeah, Mars missions or Jupiter missions, like the one that I'm on, when you go farther away from the Earth, it takes a radio signal quite a while to get to the spacecraft, and then quite a while for the spacecraft to tell you what's going on back. And so the spacecraft has to be able to take care of itself for anything that would be like threatening to its safety.
Mhm.
And good job for you to know that that is called fault protection. And the way that we design fault protection is, say you have a component that is needed for the spacecraft to know where it's pointed, something like a star tracker, which we point at the sky. It has a catalog of stars in it, and it can kind of figure out where it is. If something goes wrong with that star tracker, there's a whole bunch of different pieces of data that the spacecraft can use on board to say, oh, something's wrong with the star tracker, and it will switch to a backup star tracker and power that one on and see if it's working right. And if that one's not working right, it'll go, oh, this is not good, and it will might turn that one off too, and then use a lower level, a more kind of coarse level of attitude knowledge called an inertial measurement unit, and then power off a bunch of stuff and point its antenna at the Earth and say, "Help me! Something's wrong with me. I don't know what to do about it." And then and then it has to wait until someone on the ground can reply to it. And so that safe mode, we call it, means the spacecraft is always going to, if it's solar powered, especially, try to make sure it has its solar arrays pointed at the sun, try to make sure it has an antenna for telecom pointed at the Earth, turn off anything it doesn't need so it can be in like the lowest power use state, and then just hang out until we can go and communicate with it.
Okay, from your experience, what are some traits or some habits that people who thrive in the missions operations, what do they have that separates them?
Mm. Especially for mission operations, we need people who are deeply curious about what's going on because there might be things coming down in the data that are not obvious problems. And so we need curious people to be looking at, what is the data doing? Is it staying flat? Is it trending? Is it supposed to be flat? Is it supposed to be changing? And want to know what is going on and why does that look the way it does so that we can catch problems before they get too big. We also need people who are very calm, not too excitable. If something is going on with the spacecraft, you don't want people freaking out and running around and making it hard to kind of stay settled and focused and figuring out what's going on. We need people who are good communicators because there can be something going on with the spacecraft that you understand very well, but you need someone else to help you figure out the solution or build command products in order to command the spacecraft to do something. And if you can't communicate well with them what you think is going on and why you think that is happening, it will just slow things down. So curious, creative, calm, not too excitable, and good communicators.
Okay, so for students interested in space systems and mission design, what experiences actually translate pretty similarly to NASA work beyond like just school work or college work or anything like that?
Some of the experiences that I think are the most useful are for students who get involved in projects outside of schoolwork. Like there are robotics competitions that you can be in, and that allows you to really get your hands dirty and play with real hardware and software and make something that works. And the best things that come out of that is almost always when you try things, they don't work the first time, and you have to go and figure out why didn't that work and what can I do about it, which is a very similar thought process that we use in operations. I'm sorry if you can hear my cat, by the way. He thinks it's
No worries.
lunchtime. It's not.
Yeah. So, okay, looking back on your career, you had an amazing career. Like, what are you most proud of, not in terms of like success, but in how you grew as an engineer?
Oh, wow. That's a good question. No one ever asked me that one before.
Mhm.
I think maybe not most proud of, but the thing that I know was the most important is that when you run into a problem and you try to figure out what's going wrong, you have to resist the urge to stick with the first answer because that one might not be correct. You see
Mhm.
something, you think, oh, it's probably X, but you have to have a little more mental discipline to say, well, I think it's X, but how do I know it's X? If it's
Yeah.
X, that would also mean I should see this and this and this. Do I see this and this and this? What else could it be? Am I sure that it's not those things? Because otherwise, you might think you have a solution and implement that solution, and then the problem is still there. So I'm most glad that I was able to grow to learn how to think in that
Mhm.
way.
Okay, so for like a kind of a final question, if you like based on all your experience, if you had all that experience and then you could go back in time to like let's say you're in my shoes, turning 18 next week, about to
Yeah.
enter college in a couple of months, about to move away from the family. Um, and what kind of advice would you give yourself if you were kind of going back into my shoes?
I think I have two pieces of advice. One of them you're doing already, which is to have more conversations with people who are doing the kinds of jobs that you are interested in, so you can
Mhm.
hear a little bit more about what it's really like. So good job. You have a head start on that. I think the second thing, going into college, for some reason, I was a little bit nervous about talking to the professors. They seemed so like up here and high on a pedestal, and I didn't want to bother them. And I think I would tell myself, look, they're just people. Their whole job is to help you learn. Go and talk to them and go to their office hours and get advice from them on a regular basis instead of just when you run into a really sticky problem on homework or when you run into a deadline issue that you're worried about. Like just go talk to them, get to know them, and ask them some of the kinds of good questions that you're asking me, like what kind of things would they have told their younger selves, or what kinds of things do they most want students to learn in their classes?
So I know you did a master's at Georgia Tech. So do you recommend students doing masters or do you recommend gaining experience in the field? You like which one? There's two kind of paths there, right?
Yeah, and there's no crisp answer to that really. It kind of depends on what your undergrad education is like and what kinds of
Mhm.
things you want to do and what you're interested in. For me personally, I did my undergrad at University of Kentucky, which was great, but way back then, a long time ago, we
Mhm.
didn't really I did not participate in robotics competitions and I did not get a chance to work on small satellites and I did not get a chance to do like a major capstone project. And so I felt like I was missing something in terms of hands-on experience, even though I had a chance to do a lot of great internships. And so I wanted to do the thesis-based master's degree so that I could have that experience of having a real complicated problem to go and solve. And it felt a little bit real world, even though it was in a university setting. So if you are at an undergraduate school where you're getting to do a lot of those things, and there isn't anything in upper graduate level studies that you are like deeply interested in exploring, it's totally fine to go get some work experience and then decide later if you want your master's degree. But if you have a similar experience to mine and you want a bit more hands-on stuff, then totally go get your master's. I would also encourage students like don't pay for grad school. Don't do that. There are lots of scholarships out there, or research assistantships, or TAs, or if you start working, there are lots of companies who are willing to fund you to get your
Mhm.
master's degree. So I encourage people to not take on a lot more debt than they absolutely have to just for that.